Hello everyone, my name is Kratat Goyal and I am a research engineer on the computer vision team at Zoox. Today I am going to talk about our paper titled QuadroNet, Multitask Learning for Real-Time Semantic Depth-Aware Instant Segmentation. At Zoox, we are building a fully autonomous ground-up vehicle and are going to own and operate a fleet of them as a ride-hailing service in dense urban areas. We are also making our vehicles 100% electric to address pollution created by urban traffic. But most importantly, we are working on a fully autonomous stack to ensure that the vehicles is safer than human drivers. In the US alone, almost 40,000 people lose their lives in car crashes every year, and globally, it's more than 1.2 million. Almost all of these crashes are caused by errors in human judgment. We as a society shouldn't continue to accept this. How do we address these issues? At Zoox, we believe the answer is to make a fully electric vehicle that is built for sharing and an ecosystem to support ride hailing and ride sharing. Most importantly, this vehicle is fully autonomous. Here is an image of one of our test vehicles. Though this is not our final vehicle, from this image you can tell we have a lot of sensors and they provide us 360-degree coverage around our vehicle. As is visible from the previous image, our sensor suite is composed of multiple sensors including camera, LiDAR and radar. These sensors are quite complementary to each other as each has its own set of strengths and weaknesses. Cameras give us high resolution and color, which is useful for discerning fine gestures, small objects, and color-dependent classification like traffic lights. LiDAR gives us direct measurement of depth at a decent resolution, and radar gives us depth and velocity at pretty long distances and is robust to adverse weather. We aim to generate as much information as possible from each of these systems and combine them for redundancy. In this paper, however, we focus and learn to leverage the camera sensor data to develop a complete 3D understanding of objects of interest around us. In this figure, we show a sample input image collected from one of our vehicles, which is part of the custom autonomous driving dataset that we collected and got labeled in-house. Additionally, we show the output of the four fundamental tasks for vision for self-driving: 2D object detection, semantic and instant segmentation, as well as monocular depth estimation. The first contribution of this work is the new architecture which we title QuadroNet. It consists of a RetinaNet feature extraction backbone that gives us multi-level features as shown in the figure in blue that capture both high-level semantics as well as fine-grained structures at high resolutions. For the task of 2D detection, we then have a classification and a box regression head at every level of the feature pyramid. For the other dense pixel-wise tasks, we aggregate the feature maps at all levels of the feature pyramid. To do this, all of the feature maps are upsampled to a common high resolution and combined via summation for efficiency. We pass them to a multi-scale feature map through a dense pixel-wise encoder in order to develop more high-level semantics of the scene required for these tasks. This feature map is task agnostic and then is passed through a task specific head that outputs semantic segmentation, direction logits, and depth logits plus residuals for the depth bins. The second major contribution is the novel task formulation for instant segmentation. The pipeline of a novel formulation of instant segmentation is based on different semantic and geometric priors. An image is passed through the QuadroNet architecture, which outputs 2D detection ROIs, monocular depth estimation logits, semantic segmentation logits, and direction logits. For each 2D detection ROI is used to perform an ROI pooling on the different logits for different instant segmentation formulations. While DAIS uses both the monocular depth logit as well as the direction logits to determine instance boundaries, SAIS uses semantic and direction logits. But SDAIS uses all of monocular depth, semantic segmentation, and direction logits to aggregate support for instance segmentation. QuadroNet outputs all four jointly. Our proposed network architecture is trained end-to-end in a multitask setting. Standard joint learning multitask learning architectures typically have independent task-specific subnetworks that share only the feature extraction backbone. Such networks do not explicitly model inter-task relationship, such as the coincidence of object region boundaries and depth discontinuities. While joint training of these tasks result in improved accuracies for all of the tasks, we see greater improvements in accuracy while enforcing cross-task consistency in the manner described above. Finally, we can see that across a variety of benchmarks for semantic segmentation, 2D object detection, and monocular depth estimation, when we train tasks jointly and enforce consistencies between them, it results in better performance as we keep introducing these consistencies. Also, we see these qualitative improvements over a lot of these figures. Thanks.